Okay, we are already live.
Hi guys.
So, hi Eric, thank you very much for joining the Fab Academy Recitations. It's a pleasure to have you here. Connecting with Shenzhen is very important for us, and also connecting with the work that you are doing in Seed Studio and with all the maker movement, not only in Shenzhen but in China. It's gonna be a nice session. Students are learning how to make circuit boards, so I think it's a perfect timing, and also it's a good opportunity to start to see some products that could be developed in the Fab Lab network that can go and maybe plant a seed somewhere else with you. That I know that it's not only in China. So yeah, I think that with that, I leave you all the audience. We have the whole Fab Lab network, around 600 Fab Labs in the world, but especially the Fab Academy students, more than 300 students this year joining the program. So thank you, Eric Pang, for joining us. The world is yours.
Thank you, Thomas. And hello, all the Fab Lab students and teachers. It's a huge pleasure to be hosting the lecture today. And we're in the middle of our factory in Shenzhen. Surrounding us is a silent factory because it's middle night here in China. And I also have some guests who are the Fab Lab students from the Shenzhen. You will see them say hello to the people. And I will try to squeeze my lecture into 1.5 hours because I prepared for about 2 hours. Let me share my screen first. So it's a huge pleasure and also a big pressure for me to prepare for the contents. I know it's a bit remote and it's also a bit difficult because we also always say that hardware is hard, manufacturing always cause problems. I hope through this lecture I can give you a glimpse of what's happening back here in the center of manufacturing and give you some senses how to design from manufacturers. And I will also share all the pains and gains through the many projects we have done. So are we all good, Thomas?
Yes, perfect.
Okay.
Screen sharing working perfectly. Okay, go ahead.
So my topic today, as assigned, is electronic manufacturing. Hold on. Okay, this is me. I'm Eric Pan, and I'm founder of Seed, and also a lot of other things. Because we have done so many things, we try to categorize what is a Seed and how our business runs. We are seeing the maker community like an ecosystem, and we are playing as one tree of it. So we provide open source modules for people to do prototyping. But what we are going to talk more today is how we help people to manufacture in small volumes. And also we help to promote the culture, promote the community. And you will find out more by Googling us. First, I would like to give you not a short overview, because I think it's very important to have a different mindset growing from one piece to many pieces. We have a lot of workshops about prototyping, but just too little workshops about how to manufacture things. So if we look at the world in open hardware perspective, it's more like the pyramid. So all the makers, they have ideas, everybody has ideas, but whenever you bring them into prototype, you become the maker. You're actually growing from 0 to 0.1. But you have to go further sometimes to have the first working engineering sample. You become a very veteran maker. I think a lot of Fab Lab students are working towards this. Like I see from last lesson, you have done some PCB by Sensei, and then you'll be soldering your own devices first. But today we are going to cover how to grow from one piece to like 1,000 pieces. Whenever you have 1,000 pieces manufactured, you are actually becoming an independent product maker. You can call yourself hardware startups because you are not making one product for yourself. You're actually benefiting a larger audiences. If all stars aligns, if everything goes perfect, you might want to ramp up to 10,000 pieces. That's where the mass production actually happens. If it goes beyond that, you're actually bridging with traditional industrial resources. It's a huge gap between 0 to 10,000 pieces, but I think by step by step, all the barriers are lowered. Now everybody in all kinds of backgrounds can manufacture their own creations. And I believe a lot of you guys can make your own banner droid, but how to make an army? How to make an army that performance is the same? They can, how do you manufacture all the banner droids with some special setup of equipment, human beings, and also, more importantly, the supply chains? And I'll help you to make a better droid, but I think the concepts are basically the same. If we disassemble electronic hardware, you might see several layers. If we compare them to animals, it's like skin, skeleton, gut, and soul. A lot of you might be very familiar with soul, which is software, which has a logic, has the behaviors inside. But it has to work on some hardware, which is electronics part, the circuits. And also you need to have the skeleton, the structure to protect and form the body. And you need to make it good looking by the outer finish and also the packages. So if we want to manufacture in small volumes or bigger volumes, we are actually duplicating each of the layers. The electronics will be the focus for today. That you might very well know how to copy, download, paste the firmwares into different devices. And also you will learn in the Fab Academy how to make the mechanic parts. And also you have many ways to do the enclosure. So after we disassemble the hardware, on each of the layers, we will see this 4 steps. You start with the design. You have your idea, you turn it into a file. Then you need to prepare for the materials. You need to collect the materials in the same place and same time. And then you actually start to produce and assemble them all into one piece that can actually work. Then you need to package them into a very nice finish to send to yourself or your audiences. None of this process is easy because you need to balance between the 3 elements: the cost, the quality, and the schedule. They are very much intertwined. If you change the cost, you might affect the quality. If you want to pull in the schedule to deliver to the market faster, you might increase the cost, for example. Let's go a little bit deeper. If we talk about quality, what is the quality? There's no absolute high quality things. Quality is actually an expectation. How do you expect to get from the product? If we look at first and the right chart, you will see a lot of dots. Because the world itself is analog, the world itself is very random. You manufacture the same products with the same setup, same material. You might also have some randomness, thanks to quantum physics or anything beyond that. But what we need to focus on is to control the result inside our expectations. There are so many ways to do that. There's so many factors will contribute to the defects. There are so many systems, knowledges behind that, but we need to understand that quality is equal from the design to manufacture to deliverable. The only matter is how do you promise to deliver and how do you achieve it. So it can be affected by personnel who operates it, the materials, how to measurement to evaluate, and also what kind of machines you are using, the methods you're using, and also the environment might also affect the quality. And it might be a very nightmare for a lot of hardware startups because the schedule is always unstable. We have already seen so many Kickstarter campaigns that might delay for even more than 1 year, even cancel. So for the schedule, for the manufacturers, you have a lot of components they need to or shall arrive on time, but the supply chain is very dynamic. For example, there might be some turmoil in some countries. For example, in Tianjin port in China, there was explosive. And the result is in that port, by that time, there was an OLED shipment, and they totally destroyed in the disaster. So in the following few months, we don't have enough OLED screens. No matter how good plan you have done, these kind of disasters are out of control, and the supply chain itself is not static and might change. So we need to adapt to the changes. And also the production line has its queue, because production lines, the goal is to keep running to increase the utilization. They cannot wait for you forever. Whenever there's a new production comes, it usually needs to wait for the last batch to finish and start new ones. If there is any problem, it has to go back, wait again. And also, there are so many things that we don't know, that problems are totally unexpected. So because of the issues, before you give up, the project management is very serious. And the final thing I think is the cost. We always look at some electronics products, and we can tell the bill of material cost. You see how much is microcontrollers, how much is resistors. They don't look expensive, but we need to add a lot more cost into the manufacturing. Like the manufacturing itself, like you need to do some toolings for the manufacturing. That might be some setup fee, but you need to equalize them into the long-term manufacturings. But what's worse is behind the C-level. A lot of people don't know that they need to consider the cost of engineering. There are also so many costs on management. It's not only managing your team, it's also managing the supply chains, managing suppliers, managing all the disasters. Then you need to spend quite some cost for marketing. And also certifications, if you want to sell offline, that might be a good cost. And also logistics is becoming more expensive because of the ship hassles. And also because we are doing a lot of innovations, innovation costs because you make mistakes. The mistakes will generate defects. All the defects, they will be in your bills. So we need to be seeing them very seriously. Do you guys want to have a break? Okay. So first we start from design, because that's everything starts. That's where the karma lies. We don't. I believe a lot of you have heard design for manufacturers, because for the big companies, we usually come to the manufacturing side and they command the factories how to manufacture for them. They will also to take care of all the details. But I think for a lot of students like you, including the makers globally, our volume are very small. We are not big companies. We are not established players. We need to look at what's existing and to follow all the restraints to make our designs not only unique, but visible. So I think for design, the most important sentence is be responsible for what you have started. We see so many designs they are delivered, but they will in the end might affect a lot of processes afterwards. They might in the end affect your product. We have heard a lot of words for design, like DFX. If we categorize them into different phrases, like you might see, like developing phases, we need to design for short time to market. We need to consider for the reliability. We need to worry how to test them in the development or in the future. And then we need to worry about safety. We need to concern about how do we ensure quality. Now we need to worry about damages, corrosions, like minimum risks. Finally, we can come to production operation phase, but that's where a lot of problem happens. You need to worry about cost. You need to follow standards. You need to design for assembly, how to put them together quickly. And you need to worry about manufacturability. Your good design does that mean a good design for the manufacturing site. And then you need to worry about logistics. How do you pack them to ship them globally? And what if there are some delays? And also you need to worry about how to assemble them for electronics, how to do them in low quantity. And for the users, you need to worry about the user friendliness. I believe there are a lot of designers who are very aware of that. But how about economics, aesthetics, how to service them, how to repair them, maintain, repair, reuse, recycle. Whenever you want to dispose, how do you worry about environment? How to do recycling? How do you do remanufacturing? Please don't be frightened because I don't know of them. I got them from the Wikipedia page. We have a lot of issues because people come to the field like a software team. Software team is like a band. You might need only 3 or 5 people to come up with a design to make it working and post them on iTunes. But for hardware, you actually need a big orchestra. You need a whole team with established knowledge of about issues about DFX. So a lot of team, they come to play orchestra with a band. That causes a lot of issues because of so many things that you don't know. You know nothing. It's slow because you know nothing. You didn't know so many things that the factories didn't know that you are not a professional as their previous customers. Because we are newcomers to manufacturing, this causes a lot of problems because the inequity of knowledge. But the remedy, I think we look at manufacturing, design from it. A very important element inside of this is open hardware. We use a lot of open hardware for prototyping. Maybe on your table you have Arduino, you have Raspberry Pi, you have so many open things. But it's also a perfect tool, perfect element for you to consider the supply chains. Because you're actually sharing the supply chain with other people using the open hardware. And for next steps, I think we need to open source the manufacturing processes. So we will understand all the strengths by looking at the manufacturing process itself and come back to our laboratory to design something that matches the process. And I think that's a hope for Fab Lab, and also we are trying to do is to manufacture decentralized. It should be more like service to covering the different locations with the same process and materials. I think that's where we can make the DFX or manufacture much easier, because by different teams, different products, we are actually training ourselves and sharing the knowledges among different projects. That's a big word, but let's see the details. So this is one example from our friend called Kigali. He has the inspiration of the electronic eggs. He wants to use human beings as the electronic pets. So he has the idea about 20 years ago, but he didn't have the tools to do that. Now in 2012, he has open hardware. He tried to put together some modules to make the first prototype and a 3D print enclosure to make it working. And about 3 months later, he started to make engineering sample to shrink the size, to work with the maker groups to do a layout over again. And after half a year, he finally can use crowdfunding and essence promotions to get the idea 20 years later into market. But you see, actually, the open hardware has facilitated the whole process. Because we are having more and more platforms to suit different usages, and we have more modular sensors, actuators They are actually combined together to come up with a whole solution. And we will have more knowledge sharing and support from different channels, of course, including the CityWiki. And also we have the project inspirations from Instructables, from all people's blogs and Twitters. We are actually not only making the prototype easier, but looking at what people has done, has failed, has succeeded. We can follow their paths to facilitate the way we manufacture new things. And also, thanks to the CAD tools, they are becoming more easier to use. They are becoming free, and they are more like cloud-based. You can actually open some cloud-based CAD tools and to collaborate or find some experts to help you. If we look at them into the two-dimensional categorization, the upper ends to the right, they are more for beginners, they are more free, while on the far end is Altium, they are more professional, expensive. So we will see more involvement of the tools. I cannot tell which one suits you because you need to try them themselves and to evolve with the community. Because I think in the future, we don't need to have everyone get very professional on how to design a circuit, but you try to reuse what's existing modules and try to come up with your own complementary circuits easily. And if we look at the PCB design process, it starts from need. What do you want to do to accomplish? And whenever you have a concept, you can use some open hardware, breakout board modules to validate. And you will have the schematics to map the electronics together, and you do the layout to place the components to where they are going to be. And then you need to do the routing, verification. And whenever I think it's a very important process because that's before your manufacturing. You get your own board, like what you have done for the last session. You evaluate if it's the right design I want. But you also need to prepare for the following procedures for manufacturing, for testing, for logistics, for everything. So if everything is perfect from what you have seen for the stage, we can move on to prepare. So we need to gather all the materials together. If we look at electronic products, I will show you some examples just by my hand. But there are so many categories. We can start from a few. For electronic manufacturing, majority of the products has to start with PCB, and also the pairing stencils for solder testing. One thing for that is quality. When you make the first PCB, it might be right, but whenever you manufacture it for several thousand pieces, there might be something wrong, like even for the printing of the sticker screens. But I think for a lot of us, the major issues are on the components, both on the active and passive ones, like the ICs, like the resistors, capacitors, because you might meet issues on lead time and also quality. And for the lesser risk ones are the standard mechanic components, like the rivets, the screws, nuts. And also for the standard accessories, they might be very low risk as well, because it's very substitutional. And for the packaging materials, you need to consider it because it's part of your product. But it might also affect a lot on quality. The materials you use, the printing, the quality, the color, that might differ from what you have thinking. But what's worse, I might try to convince you not to do that, is customized parts. You might spend quite enough preparations and time because this customized part, they might need to lead time. They might delay the whole project. But more importantly, they might cause tolerance issues. You will very soon meet that kind of issue whenever you have your first enclosure to your electronic board, because you might want to have enough buffers to make sure the large massively customized parts. They are consistent, and all the tolerances they can align to each other. And if you really want to do injection molding, that's the most difficult one because you will spend a lot of money, and the lead time are usually over several months, and then you might in the end to cover with tolerances. Okay, don't get too frightened because we will see the bill of material template. This is very normal, very simple one. We don't have so many items on it, but that's actually how do you describe the things on your electronic board. You might have seen the bill of materials, but in real manufacturing, if you give the task to someone on the other side of the planet, you might make sure everything is right, everything is clear, and make everything is feasible. I will send the slide later so you can look into the details yourself. But there are some hints for the bill of material DFM. Please don't assume people knows what you know. I've seen so many bill of materials, they tell people, oh, here we need some screws. That's it. But how could I know what kind of screws you want unless I have the samples, unless I measure it? So don't assume people knows. And you need to always have a plan B. What if the components you used, they are extinct? There are very usually we just take some components on our desks, or sometimes we unsolder them from other product. But that component might be extinct, unavailable. So try to have a plan B. And whenever you are preparing for the bone, please leave no room for ambiguity. You need to make sure if you are talking about IC, you including all the package details. If it's industrial grade or it's just something that works. You need to be very, very clear. Imagine that you are working with a computer without too good AI. And you need to, in the long run, consider availability. We see so many projects that they use some components that just randomly, and in the end, they cannot get from the suppliers, or the suppliers might need several months to provide the ICs to them. For small volume, that might be a less issue because you always can find some small volume ready stock. But if you are manufacturing several 10,000 pieces, 1 million of them, you need to make good relationship, good plan with your supplier. So bill of materials, they are very routine problem to your manufacturing problems. So we look at PCB. PCB are actually easy because they are very standardized and they are very digital. Whenever you bring a PCB into production, I think you will learn later in Fab Academy is to different layers, 6 screens, solder mask, copper, etc. And here's a video. If you don't have the video is too much latency, you can open the links on the end of the slide. So this is one way of manufacturing PCB, but there are new other ways besides the homebrew PCB. We will see like Watera, they are trying to like ink print the circuits, and we have other mills, or you can use some desktop CNC to cut low precision PCB as well. But for PCB, we also have some hints for design for manufacturer. You need to look at the supplier's process spec. If your supplier is your CNC machine, you should look very carefully on the precisions it has. If you use some fab house to do the PCB, you need to look at their spec, and you need to leave some buffer if possible, because that will increase the yield of the PCB. And whenever you're designing the PCB, you need to worry in the future how people can assemble the components onto the PCB. So you need to make sure the components that needs to be polarized must be marked clearly. Excuse me. Okay, this is a pain for me, because there are so many projects that reversed components cause defects. And also, to make the life easier, you try to have the signature for each component. If you cannot put them onto the PCB itself, you better to have a paper printing the matching marks. And also, I think this is something different, that the silk screen is very much more important for the open hardware world, because we are usually shipping with the PCB only. So the silk screen has to be clear. But to do that well, you need to control them in like 6 mil width and 40 mil height. That's something you can guarantee the printing quality. And also, after you have the PCB, you want to bring in to manufacturing, you need to have the stencils. It's very similar to the silk screen printing, but now you are printing with solder. And for each of the products, you might have a different stencil. That causes a lot of waste. It's very critical. And we have also a room of all the stencils used and expired. And you might be very clear about the active passive components, but I don't have enough time to explain into more details. One rule is try to use the popular components. Where can you find the popular components? One simple way is to find the most popular open hardware board. You see what components they are using and try to reuse the components they use. Like, for example, Atomica 328. That's something you might want to share. And for the regular resistors, capacitors, that should be no problem. But if you choose a button, try to use very standard, very popular button, or you might be jammed for a damn button. We have some example here. Is we try to calculate. Among the projects we have done, the most popular 100 components, they consist averagely 30% of the biomaterials, which means sharing the library can sharing the supply chains. They can reduce cost, lead time, quality, and it's a way for people to share the knowledges. Like Exprino, it was a project we have done for a Kickstarter campaign before a long time ago. It starts from PO order to shipping for some pieces in only 20 days. The only reason is that he uses a lot of the common, very popular parts. We will go into more details, and we have a new library called Open Parts Library, and also our friend Octopaths, they create an Open Parts Library. You will always try to work with the community to select the most popular one. And also we will have more standardized accessories, because they're too standardized. If for small volume, you don't worry about them. But if you are in a larger volume, you might find the suitable factory and make a long-term delivery plan with them, and to make sure all the qualities aligns your specification. And also packaging is something that you cannot avoid, and it will totally affect, but it's not the importance of our topic today. But remember, it's also part of your biomaterials. You might want to include the static plastic bag. You want to include the stickers, everything into your biomaterials. Or you might be waiting for them to get the whole project. And then for customized projects, I can give you an example that we're trying to align the mass produce, the mass factories with our laboratory, which means if we can customize in our own equipment, and we find the factory has thousands of the same equipments, it's much easier for the customers' customized parts to get duplicated. And also for injection molding, I think it's a very painful process to introduce, so we leave it for some other time. And finally, imagine that we are cookers, we are chefs. We have all the ingredients lying on the table. And the nightmare, the real nervous moment has come, is whenever you assemble. Only by assemble you can find a lot of the mistakes. You can understand, oh, I have bought the wrong materials. It's not fun. And if we look at the whole assembly and test process, they can be very complex. But why are we doing assembly and test? Is that you don't want to do it yourself. You have to make these tasks as easy, as repeatable as possible, and give someone you don't know to accomplish them. And if people don't know you, they need to follow some programs. We are actually talking with all the files, with all the SOP, standard operation procedures, to make sure we have the right deliverables which match our expectation. So it's very important, and we need to respect the whole progress, or you will be affected by what you have studied. Okay, another little video. So this is how we put the solder paste onto the PCB board. The first layer is the stencil, and the solder will just go down to infiltrate into the PCB itself. So that's very simple, but this also requires a lot of precision, and the way you do the stencil might affect the result. And to pick and place machine, and also for reflow. So you might already seen the pick and place machine. They're actually doing something very simple, is put the components onto the PCB, which has already the solder paste. But imagine that you have to put so many components onto so many PCB, and to make sure they have the same result, to make sure they are fast enough to save time, to make sure they don't make stupid mistakes. So you will see on the screen they have some optic alignment. This is smart point, and this is the pick and place height. Sorry, because it's a bit dark. So on the bottom of the screen, there are actually reels of components. Please, if you have time, watch the video over and over again, because you will know how the machines work. And on the other hand, you can design according to performances, according to the behavior of the machines. So whenever I finish pick and place, they are like glued to the PCB. They will do a visual inspection to make sure most of the things are right. But they are like upgrade. They need to be cooked. And if there are something like too big to fit into the pick and place machine, sometimes for small volume, we use hand manually to put them onto the board again. And that's the oven. It's actually an oven, but with more precise temperature control. After going through the oven, we mostly finish the assembly process because all the components are in place with the electronic circuit board. And they will do that again the QC check. I will show you some examples. Why do we need to do so many steps to control quality? So as we just explained, the reflowing oven is an oven. So it has a, but it's the difference is they have several zones. Actually, the more heating zones the reflowing oven has, it can be controlled more precisely. So it has preheatings to make sure they are warming up, and then thermothoc, so to make sure all the components they are warm up to an extent that ready to be reflowed. And in the okay, I don't think I'm going to explain so much about that, because that you can dig into the details, but that won't affect much about what you have done for design. But it's good to know. And also, more important is for us to understand the issues. We are sorting the issues. The biggest issue for SMT is like tone. The SMT, they should line perfectly on the surface, but sometimes one end comes up because the components might not match the dimension of the actual design, which means the PCB, the footprint does not fit into the component itself. So making sure the pad matches the package of the components. And also we have some soldering, which means the soldering is not stable, is not totally heated. The cause is actually the pitch. They are not matching the components dimensions. And also there are some through-hole pads that cause inequity of the physical elements. So the solution is to design from actual packages and to avoid holes of the pad. So from this we can see a lot of the QC process is to check out, to find out these issues. But the reason usually causes these issues are from your design. So you might get your design working in first piece, but imagine in the long run, in a more complex process on the other side of the planet, they might have more issues than you expected. And also we have more problems, like there is no mark on the pads. So there might be some errors if we have to process manually. And there might be some mismatch between design and the pads, causing some problems in the manufacturing. So these are some specific cases, but generally speaking, I think we need to have some compassion for machines. Machines are not slaves, they are our partners, they are helping ourselves. So we need to understand how the machines work, and we comply ourselves to try to collaborate with the machines to make sure our designs can be very easily done by the machines. From that, we can have one more tips, which is we need to align the same components in adjacent order. For example, we can see from the video, the pick and place machine actually are getting the components from the rails and then put them onto the board. So if we are targeting to the same rails, they can be much faster than switching to different ones. And you will try to leave enough margin to the edge of the PCB, because there will be some, you will see some belt on the edge of the the belt. There might be some grippers. So if you put the components too close to the edge, they might be moved. And also, you will see that during the video, inside of the video, we're actually soldering them on one side, which means if you put the components, even if one components on the other side, we need to do it over again. So let's try to put all the SMT parts on one side of the board. And especially for the open hardware community, we are having more through-hole soldering than everyone else. It's easy for hand soldering to verify in the very beginning of the process, but it's actually difficult. This is a semi-auto through-hole soldering machine. I don't need to explain to you how to solder them because you can do it yourself, but it's actually a solder part. All the boards, whenever they're placed in the right spot, they sink into the heated solder and come out. So we always see that electronic manufacturing is very close to cooking. It's a part that actually makes this mature. It has to stay in the hot solder for quite a while. You will see the smokes. They are crying, but that's their destiny. And for a while, they come up again. Okay, perfectly soldered, or we can say it's like glued. And be sure to wear some gloves because it's very hot. And I think the process are evolving as well because you cannot avoid. Sometimes you have the two big components. Sometimes you have the pin headers, and we have some automatic soldering machine, and this is one of them. So this is this is like robots. You may see that they require some specific fixtures, and you also need to program it. Okay, I can watch it over and over again. So for through-hole soldering, we have also a lot of pins. Like I didn't add is a more usual way is wave soldering. It's very much like an oven. There's a belt. It comes in. There are hot solder underneath. So sometimes the components cannot be wave soldered because they are their design might affect the process. And sometimes the components cannot be soldered by hand because there are round through-hole dimensions. The holes are too small that you cannot insert the components inside. Or maybe you are buying different benches of the components that they cannot fit into your old designs. So you need to make sure all the dimensions they align. And also they might be too short distance between two components. And they might even, either it's for machine or for human beings, it's difficult to solder. And also there are some tilted parts after with soldering. You might need to strengthen them by some tabs or by some extra support. So for DFM, I think if we can come back, if there is another chance for you to design, you need to keep space for each components, at least 0.5 millimeters. And you need to ensure the space is enough for manually soldering, repairing, or even verifying. And more importantly, please avoid through-hole soldering if you can, because it really does not fit for mass productions. I think we can have like a 10 minutes break here. We can extend. We can come back about 10. I don't know time, but it's like 23 o'clock. Yeah, we come back about in 10 minutes, and we can keep posting comments. Yeah. Okay.
Okay. But how long do you think we were?
I think
we're missing completely.
I think we can finish it in another 20 minutes.
Okay, we're trying to.
Or I think just go on.
Yeah, I think we should go on. I think it's better.
Okay.
Because it's one single video.
Okay, so anyone who
okay for you.
Excuse from lessons, go for yourself, and I will carry on. So the chapter 4.
Thank you.
Is we come to test and package, which is actually sort of to the end of the whole process. Very importantly, why do we need to test? There are quite some projects come over to us, and they didn't know what is a test plan. They didn't know how to verify their plans. It's just, oh, just assemble them and send back to me. But it's very, very critical in the whole manufacturing process to have the test. And how is test made? They actually, if we see all the tests simply, they actually control how to activate your circuit to make it working. And also you need to give it's some simulations. It's actually like giving a VR goggle to the circuit board to make sure understanding, oh, I'm doing this. Then it will output some results. You need to judge if the result matches what you have expected. It's very simple, but the reality is very complex. This is before we do mass production. We need to do a lot of verifications to make sure the first sample, they will be working. But this is just a start. We will have some performances, we have some functionalities we need to verify, but you need to design a plan to accomplish that. There are so many test methods and priorities. Priority means how important it is to us, supposedly to the simple open hardware projects. PCB inspection systems, there'll be like e-test, there'll be some visual inspection. We don't need to worry much about that because they are usually done by suppliers. Secondly, there'll be ICT. It's called in-circuit test. It's very common for simple projects, and it will be, we have used a lot of them, and you might be using that. And also we have some functional testing. They are more for complex projects like IC or wireless things. And also for complex logic systems, you might have some JTAG boundary scan testing. I think if you have some system like Android project, you might be using that because there's a very difficult way for you to measure all the memories, etc. But for usual test, you need to combine some of the testings to make sure you cover all aspects of your project. So what is a good test plan? I think I have asked some experts and they don't give me good answer. I'm trying to summarize like this. So a good test plan is actually a killer. It's a good killer of defects. The most important rule is like a firewall. No underkill. Underkill means it's a defect, but the test plan does not tell it's a defect. Let it go. So it has to make sure it excludes all the defects. But whenever you have all the test means to make sure the quality, but you don't want to have too much overkill. Overkill means it's a good project, it's a good product, but you might set in some threshold too tight, or it might be disturbed by external elements that you think is wrong. So we need to be, the best is we examine the units with once, and we tell the good from the bad for once. And the testing has to be fast. It's very important that we don't want to, in the manufacturing floor, to use half an hour to test one device. You need to have all kinds of means to fasten the process of testing. And it has to be easy because the operators, they are not engineers yet. They don't know what they are thinking. They don't know your product because they might be working with so many projects. So the best is to have as easy as possible, like one button result, good, no good, that's it. And the test plan has to be cheap because test plan are usually the test jigs, the fixture, the SOP, the operations, how to do that, and the program. Especially for the test fixture, you don't want to spend too much money on that because you might make a lot of them to manufacture more of the products. For example, if we might have very fast pick and place machines, but whenever you are testing them, how fast can you test 1,000 pieces, 10,000 pieces? One test fixture might not be enough. you might need 10, or you might need to penalize your products so that the test fixture can test 10 pieces at one time, for example. So bear this in mind. And this is the legendary test jig. There's no rocket science inside. You open it up, it might be just an Arduino. And to the left of you, is what you see when it's operating. It's better to have some buttons, the basic UI. I know you guys are very good at that. And also better to have some screen, or maybe in the future we have some wireless network to collect the results. And what we show here is handle. So it's a manual testing fixture. It's cheap, but whenever it goes large volumes, it can be automatic. And I suggest in the future, you might want to design the test fixture as you are designing the product. So the test fixture can be as simple as Arduino with some special circuits to measure the input, output, the voltage, current, etc. And you can use some laser cutter CNC to make the box. You can make it much cooler. This is just some enclosure we get from the local supplier. And the most precise thing is on the test bed. It's like needles on the bed, but you need to very precise holes to make sure they match to your product. And here is packaging with the standard operation procedure. Please don't forget the packaging is something you also need to design very carefully, because it will affect a lot on how to assemble them and how to ship them to protect the product, to make it good looking, for your user to do a good unboxing. I'm not seeing the packaging for your phone is a good one because it's taking too long. It's more than just to put things into a box. You need to put them with a sequence, and you need to make sure everything is placed on the right direction. People might make mistakes, but we can design to make sure nobody can make mistakes. So, sorry, this will be jumping. So for the testing, sometimes we cannot make a test jig because there's no test plan for design. We need to really consider it. And for just we can see the assembly is a process, and we need to make sure that we not only the designer ourselves, we do it by ourselves, but we could also ask someone else to do the assembly according to your given instructions to make sure they are executable. And for packaging, people might not know how to package them because there's no clear instructions. And also we meet a lot of unreasonable packaging methods. So generally, for assembly and test, we will try to involve less process, which means if we can avoid through-hole assembly, we don't do through-hole, and we make each process count. And also we need to have the SOP, standard operation procedure. It's very critical. It's like programming. This might be impolite, but you're actually programming someone else to make sure he follows your expectation to accomplish the manufacturing process. Of course, they can help you to improve it, but you need to think in their shoes. And we try not to invent in the process unless there is a very critical reasons. And whenever we are manufacturing in large volumes, we'll do a pilot run, like for manufacturing for small volume, like 100 pieces. But don't expect the pilot run will expose every error, because it's just 100 pieces, and it might only cover a small fraction of the basic problems. And there is a doom. Whenever there might be problem, you avoid it, there will be problem. So don't overlook any possible risks. And okay, thanks, Thomas. We are coming to our takeaway. So let's go back to the whole process. It's actually the 3 steps. We need to do the designing, to prepare for the engineering. It might take 1 to 30 days, because there might be unclear bone, because the process tolerance is too different from manufacturing. We cannot manufacture them, and there are usually inadequate test plans. Whenever the engineering is ready, we do the setup, we buy the components. That's causing a lot of delays, because of the long lead time components. They might take a few months to buy. And also we have consistency problems. Consistency problem means you are buying 100 like a school, but the schools, they are not like each other. And also sometimes we have too complex supply chains that we need a lot of logistic issues to make sure they arrive in the same place in the same time, like reporting to the customs to make sure they follow a lot of standards. Whenever we are doing manufacturing, it's actually quick. It can be 3 days, sometimes it can be even like half a day, because there are so many unexpected errors that might cause a delay up to 2 weeks. And very usually for the small batch, for the initial batch, you will have no yield. Means you are manufacturing like 1,000 units and you only have 500 out of them. And also you might have uncontrollable assembly time, because the SOP is not clear enough. The assembly process is not easy enough. So it's a very difficult process to bring the prototype into product. But as long as we respect for the elements, it can be done easier and easier than before. So if we can categorize the things we need to do and what the suppliers need to do, you can refer to the chart. I think I'm not going to read them, but you need to watch the slides afterwards. And you really need to consider in the shoes of a supplier to make sure what you have delivered, they can start something good. And tips, again, for indie products for several thousands, there are 5 simple tips. First is we need to balance cost, quality, schedule, and we need to consider the overall cost. It's not only the material cost, it's everything. It also includes your time. And we need to use the popular components to avoid all the risks or the problems. Also, we try to involve fewer processes as possible. And this might be a stereotype, but please try to use SMD components if possible. Okay, I'm not sure I have the right to leave some homeworks, but I will leave you some practices and you may try to do that. So I have done this in the last Open Hardware Summit. It's a very important process to try manufacture something yourself. Let's start with something easy. I believe there are a lot of good designers among you guys, and how about let's redefine the hat. We can put more people in into different teams, or if you are in an app, you can divide into several teams. But you need to worry about these things: the cost, how many basic materials per hand you have used, and the volumes, how many hands you have manufactured. And also you need to keeps the consistency among the same batch. And also, you need to promise, which means what you have pitched to people, like what you have done a Kickstarter campaign, you need to actually give them something very close. You know what I mean? And also, you need to vote for the style, to vote for, okay, this is popular. So let's start with something basic. I believe you all have some A4 paper with you or around you. How about we take 20 pieces A4 paper and with one adhesive tape. And we can also use anything else you can find, but don't do it illegal. And you use some equipment, which are scissors, stapler, and use some color pens. Given this material and equipment, how can we manufacture? So I have done this workshop. It's like within 1 hour, so it's not too terrible homework. You might spend 15 minutes to design among your teams, and also you pitch to the people, or you can just leave some message. What are you going to deliver to the people? And you need to spend only 20 minutes to manufacture the hats you want, and try to manufacture as much as possible to make them consistent. You cannot make yourself because it's not fast enough. You have to teamwork. You have to authorize the job to someone else. So you need to have a very clear SOP to teach people how to turn A4 paper into the hat you want. So finally, we will have deliver. Like we can put all the hats together, take a picture. Are these hats have good quality? Are they matching what we have promised? So we will have more details in objectives, but to save some time, I'm not going to more details. The major objective for design is to make the first hat, the engineering sample, and for pitch, to sell the designs to the bankers, and for manufacturing, manufacture more, but make sure they have the good quality. And also show us the results. You can share the results, the photos, thoughts via Twitter. You can add the studio Twitter account, hashtag Fusion to win. For anyone submit this, we will give you a free PCB coupon. For the winner, we will give you a PCBA coupon for you to try the small batch electronic manufacturing. So because I'm not sure if I can give you homework, this is just a practice you can try. And also, I think this lesson is coming to an end. Please have a good luck to the math, and don't make the math into a mess. And also, I attached most of the component information into the slides, which I have already shared in the Google Plus group. And I think we have some spare time as we. Let me switch back into the video.
Perfect. Thank you very much, Eric. I don't know if you noticed that Neil is just joining us.
Hi, Neil.
So, Neil.
Hi, Eric.
Long time. Good to see you.
Good to see you.
Yeah,
So,
we are in the middle of our factory.
Sorry, say it again.
We are just inside our factory. So I choose this place to do the lecture because after the lessons, if people are interested, I can show around the real machines and also the real things in the manufacturing floor to give you more perspective. And also, I'm open to more questions. I'm not sure I can answer all of them, but I will try.
So I'll start. I have 2 questions, but to start, just do a quick pan around so we can see the scene where you are.
Yeah. So let me try to. So because it's the middle light.
And also who you are with.
Here. Yes. We start with the audiences. We have the Fab Labs students from Shenzhen because they are so they don't want to go through VPN to Google Hangout and come back, so they move their atoms to our factory. So this is our factory, and you will see they are also trying to do the homework of last session. Some of the sensei are doing good, and some are not. And also we will show you some of the things we are manufacturing.
Oh, Eric, you're mute, and we lost your video. Oops.
Give him a minute to come back.
Yeah, that's it. Send him a note.
How many viewers are there, Tomas?
At the moment, 95.
That's great.
The max was 110, actually.
That's great.
Okay. You're back, Eric.
Okay, I'm back.
Okay.
So you will see, like this is both halfly assembled. They are fresh. They are equivalent, and also we have the test fixture, which we use this kind of fixture to test electronic boards. And you will see it's usually underneath is Arduino based, so people can change it very easily. And that's a live stencil we use to manufacture this board. And you will see all the components used for them. They are big hassle, but we need to prepare them. It's like the ingredients for cooking. And say hi to the teams again.
Hi.
And so a little quick pan around. That's the factory we are having, and it's empty because people are not working overnight.
So,
And that's the machine we're talking about. So this is where we put in the PCB board, and this is where we put a solder paste onto the board. It's silent. It's sleeping. And that's a pick and place machine. You see all the rails, each of them is one component, and you will see more rails on the other side. And you will see more like there are like magazines on the other side. So we have a lot of spare component rails because feeders because we want to shorten the process of switching. And you see all that's our library of stencils. So each of them is one product, and this is most of the company use the components, but I have suggested you guys is to try to reuse popular components as possible. And whenever it goes to oh, perfect. So here we see this is some info for people to see the layout, and whenever they're putting the components onto the board, there are some marks like they will match the components according to bill materials, and here are like some SOP. So it's the basic operation manual for people to follow, and that's the entrance to the hill, which will be heated to 300 or 200 to 300 Celsius. So that's flow oven, and after the flow oven, people will verify them. So you will see some in-process board.
great. Okay, let's get to some questions now.
Yeah, please.
So first, what time is it?
Sorry?
What time is it there?
Oh, it's 11 p.m. So we're having our Yuanxia festival, which is the middle night.
Good. Thank you for staying for us. So I have a smaller question and a bigger one. The smaller one is if somebody from the Fab Academy wants to work with you and Seed to transition to commercialization, what's the right way to work with you? How should they contact Seed?
I think in the future they have to go through the lecture first to understand all the problems for design for manufacturing.
Right.
And of course, they can contact us by so many means. They can just go to our website.
Well, that's what I want to say. So they've come to your lecture. They'll do a final project. They've been reviewed. Everything's nicely set. What's the best way for them to contact Seed at that point?
I'm joining the Google Plus group. They can just find me there. Also, they can In the slide, I will leave a message, contact a special email box so people can just write.
Okay, good. Add that.
Also, Neil, one comment on that is like we have one product actually going from the Fab Academy to see this Smart Citizen. You can announce
great.
that. Right. Yeah.
Okay, now here's the bigger question. Fab 12 is coming to Shenzhen.
Oh, I forgot to say welcome.
Well,
So
but more than that. No, but that's too easy. I'm going to make it harder.
Okay.
You did a great job about transitioning from prototype to mass manufacturing.
Thank you.
The goal for me at Fab 12 is the transition to Fab Labs 2.0, of Fab Labs make Fab Labs.
Yeah.
And so if Fab Labs make Fab Labs, and if Barcelona and all the other Fab cities produce everything they consume, there's still an important role for Shenzhen, but it's different. So you did talk about the roadmap from mass to personal manufacturing. So if every city has rapid prototyping tools, today we send everything to you to make. In 20 years, we'll assemble the atoms. But talk a little bit about the roadmap from mass to volume personal manufacturing to distributed manufacturing to the Fab 12 vision.
I see. We believe very deeply on that as well. So that's why we established our first offshore manufacturing center in California. We're trying to do more. As you might see on my back, there is a cell we call Cell 0. It's a very small team that can do everything from electronics to mechanics, and also to introduce the first engineering sample to 100 units. I think from 1 to 100 it should happen very close to the makers, to the Fab Lab neighborhoods. And then it can be ramped up with established experiences. And it's also very important for the small volume manufacturing to match to the local needs. So we can make a smart table, but we don't need to manufacture everything offshore and ship it back. We can make the core components maybe in large volume, but distribute them into different locations. And for example, in Barcelona, we use some wood and to make the very unique furniture, put the electronics inside, and that's something different. So I think we are totally willing to explore the possibility to work with FEM 2.0.
Yeah, let me encourage you to stay in touch. Tomas is coordinating the emerging Fab cities, the cities moving towards self-sufficiency. And so we're really sort of building this whole global fabrication on demand. And so I think Fab 12 is both an opportunity and a homework assignment to get ready to support that.
Okay.
Okay.
Yeah,
we have homework.
Oh, that's my homework. Okay.
Yeah, that's your homework. And then here's my last question. You gave an impressive talk about what you can do. What can't you do? What limits you? What are you frustrated by?
There are too many things I can't do, because you see the manufacturing. If you look at things around us, I always feel frustrated, because we have been talking about the makers, Fab Lab for so many years, and there are so many things we still cannot do. You look at the TV underneath, we cannot manufacture it because it's too complex. But I think it needs a lot of more collaborations, and to increase the process we can use, and also to open up the supply chain so everyone can use that. And thanks to the economic recessions, we have more factories, supply chains who wants to open to work with independent product makers. I think it's a good trend, and we are trying to push the trend further. And answering to your questions, and I think we are doing some the joint area of different industries, but for each industry, they are very, very professional. We'll try to build synergies with them, and so what they are good at is something we can't do and we don't need to do.
Okay, good. Well, thank you for joining. I look forward to seeing you in Shenzhen. I'll now drop off and listen to the stream as Tomas reads questions that have been posted.
Okay.
See you.
Thank you. Thank you, Neil. Thanks so much, Eric. It was amazing talk, and a lot of synergies. People is starting to post questions. I'm gonna go first, and before giving them some time for more questions. I want to maybe ask you about something that you showed me. You were starting last year when I visited you, the Internet of Things platform you were developing. Maybe you can talk about that a little bit. The data,
the whole idea starts from a reform. Maybe you have seen this one.
Mm-hmm.
So it's a modular phone, and it's actually the toolkit we want to create for people to build their IoT stuff. And this is just a start. We want to build more solutions, so people can just come to get the whole package and have something that is working. But on all aspects, from the electronics to software to mechanics, they are open, so people can change it. And we want to lower the barrier for IoT because it was too difficult to go from atoms to cloud. And what if we can give people something ready to use, like a template, like a WordPress, that you can just change it. So we are cooking more, and you can always find us on Kickstarter, and we will be releasing more IoT solutions this year. And of course, please tell me what you want, and we will totally consider that.
Okay, that's fantastic. Another question that maybe for people to understand, and since you founded the first makerspace in Shenzhen, if you can tell us how many years ago you founded it, and how many makerspaces there were in Shenzhen last year, and how many makerspaces are today, to understand the growth.
It's a very fun answer. I started the makerspace in 2011. By that time, we were too lonely, and we come to California, and we are totally jealous about the makerspaces, and say, oh, why don't we do one? And I met some local makers. They don't know they are makers, but they are makers. So I used our previous office as a makerspace and open to the public. So that's where everything started. And we also bring more events, more interactions. But until I think 1 year ago, there were less than 4 makerspaces in Shenzhen. I think three. Mm-hmm. But after the Prime Minister came over, I think this year we have more than 200 in Shenzhen. And we are checking there are more than 200 places called the makerspace in Shenzhen. And I'm saying that maybe there are more makerspaces than makers. So I think it's a good place for me to say this. In Shenzhen, we are totally in short of makers. Please come.
We're gonna bring you more than probably around 2,000 makers from the world in August, for sure. So Anna is asking about the electronic furniture that SID is developing in collaboration with Barcelona. That was an example, Anna. But actually, it's not existing yet, but probably something that we can do, right?
A pleasure.
Okay, I don't know if anyone have more questions. I think we're reaching to our max of duration of the Hangout. Please post any questions if you are eager to ask something to Eric. Otherwise, you know that we are going to visit you. Let's make maybe an easy one. We will be able to visit SID Studio while in Shenzhen.
Okay, we'll prepare some open days and workshops. We're totally get ready Shenzhen for your visit.
Well, I mean, that brings an interesting thing, which is, let's see what happens in the Fab Academy. We're expecting for this year to be the year in which more and more developed and let's say relevant projects will be created. We're really going to push for more and better projects. And it's going to be interesting connection with SID Studio. And I encourage the Fab Academy students to come to Shenzhen with a business proposal probably to SID Studio.
So a little update. What you are seeing here, I think it's last week because we are moving to a new factory. I will welcome you to our new factory, and also the makerspace will expand to a much bigger venue with more equipment. So, and of course I will talk with you how to make it sure the new makerspace aligns with the Fab Labs send us to join the network.
That's
So
fantastic.
hope to see you all in Shenzhen. And whenever you guys are nearby, please drop us a message, and we'll come to check out. And feel free to write us emails, Twitter, Facebook. We are all open, and we live beyond firewalls. Yeah.
Thank you very much, Eric. And likewise, I mean, for you, when you come back to Europe, let's make sure we meet in Barcelona or somewhere else. And thank you very much for joining the Fab Academy program. And we hope to see you very soon in Shenzhen. We're going to be there very soon. Okay.
Thank you, and have a good day. Good night. Bye bye.
Okay. Good night. Have a good sleep. Bye, guys. Good luck with your week assignment. Ciao, ciao.
Cool. Bye.
Bye, everyone. Have a good week.